Hi, today I'd like to talk to you about a, a method for helping us understand what's going on with COVID. And I'll be using a method called Zipf's law. Now, the major theme of this talk is suiting the name of the organization is Outliers. And that is quite often you can find out in a data set what is going on by looking at outliers and trying to understand why. What happened to a particular observation that made it so much bigger or so much smaller than what we'd expect. And so in this talk, we'll be guided by the observations of three epistemologists, wise men all. The first is Henny Youngman, who pointed out when asked, how's your wife? He said, compared to what? He was trying to explain that you don't know anything absolutely or very rarely, and it always has to be compared to what. The second is by a second epistemologist named Yogi Berra, who said, he talked about the importance of graphics, and he said that you can see a lot just by looking. And third is a famous University of Chicago statistician named David Wallace, who pointed out that the second step in analyzing frequency data is to take their antilogs. You'll see where their advice comes in all the way through the talk. First, let me tell you about Zipf's law. It was formulated by George Kingsley Zipf in the middle of the 20th century. He was a linguist, and he was studying the use of words in various languages. And he knew that some words got used a lot and other words get used very rarely. So for example, in English, the and get used a lot, and words like bitty cat don't get used very often at all. And so he said, if you take a whole corpus of words, a whole book or many books, and you keep track of how often each word is used, you can get the rank of that word. So the word with the highest rank is the one that's used the most. The word with the second highest rank is the word that's used the second most, and so on. So X1 might be the rank of the in English, and XN might be the rank of bitty cat in English. And what he discovered is that if you make a graph of the rank of the words against the log of their frequency, the log of how often the word shows up, it turns out to be linear so often that it's disquieting. Now, he just looked at it with many different languages, and it always turned out to be linear. I'm going to show you some other examples that are not language. So, for example, in the Prussian army, they kept track of how many people in the Prussian army were killed due to horse kicks. That's not very similar to the word usage. And so you can see that the year with the most deaths due to horse kicks is here, and the least is there. And this is the log of the number of deaths. And you can see it's basically linear. Who would have thought it? And then there was a paper that looked at the relationship between malignant melanomas and sunspot activity. And we discovered that sunspots are also follow Zipf's law. That is, the year with the most sunspots is here, with the least sunspots is there. And this is the log of the number of sunspots, and it's dead linear. It works for everything. So for example, in 1990, the College Board made a survey of various majors in college and how popular they were, how many kids was majoring in them. And so along this axis, the x-axis, you can see this is health and allied services as the most popular major. Engineering was somewhat less, and education somewhat less, and home economics is much less common, and the least common one is library and archival sciences. And if you make a plot of the rank of the major versus the log of their popularity, it is dead linear, except for library and archival sciences. That seems unusually small. Now, we only know that it's unusually small because we know what to compare it to. Compared to what? Compared to what it should have been. So it should have been here if it was following the same sorts of law that everything else is, but it isn't. So this has been brought to our attention as something special. Now, Zipf's law even works for very small samples. This was a task force on statistics in the American Psychological Association, and it was a meeting of the 10 members of that task force. Now, these things, anyone who's ever been to a meeting like this knows how mind-numbing it is. And so I spent my time while I was there just keeping track of how many times other people spoke, just a way of keeping from falling asleep. And it turns out that the person who spoke the most, her rank was 1. And this is the person who spoke the least, and his rank is 10. And the log of the frequency follows Zipf's law, exactly the way you'd expect. So even with very small samples, it works. Now, an interesting example, well, the next question we have to ask is, what does it mean when Zipf's law doesn't hold? It seems to hold all the time. So here's another example, and this is the participation in the New York Marathon by the country of origin. And so you can see that in the New York Marathon, the country with by far the most entrants is the US, and then after that it's France and Italy and Germany and so on. And you can see that with the exception of the US, all the others follow Zipf's law. So the second rank, third rank, fourth rank are easily predict what the log of the number of entrants is going to be. Well, when we see this outlier, this unusual point for the US, we have a story for it. And it says, you know, why is it so many more? Well, because the marathon is being held in the US, and so you'd expect a lot more entrants there than from any other country. Not just more, but a lot more. And this is supported when you break down this idea that distance is what's mattering. And this is supported when you break down the entrants in the New York Marathon by just from the US and look at what state they came from. And as you might expect, New York State had the most entrants, New Jersey second, and all the other states, at least all the others that are listed here, followed Zipf's law. So once again, we see a deviation from Zipf's law with New Jersey or New York, and that suggests to us that there should be a reason. This is unusual. And so what's going on with New York compared to what? And of course, you can see this by looking. Again, so now we've used the wisdom both of Henny Youngman and Yogi Berra, and we're looking at it by the log of the number of cases, and so David Wallace enters in as well. So what about COVID? What does that help us about COVID? Well, here the number of reported cases for COVID for 171 countries of the world, and these data are from December 6th. And so we rank them from the country with the most COVID cases down to the country with the fewest. And you can see that when you do this, this is their rank, and this is the log of the number of cases. It follows Zipf's law. It's a straight line, except for these three, the US, India, and Brazil. And so the natural question is, what are they doing that's different? Both the US, India, and Brazil all had policies for dealing with the pandemic that differ from the approach taken by most other countries of the world. And this plot suggests that those approaches have had unfortunate circumstances and consequences. But however, I should point out that these are reported COVID cases. Since then, we've learned that some countries like Russia and China may not have been accurate in their reportage. This was an article in the New York Times on December 30th, saying that the number of deaths in Russia, and of course the number of deaths is related directly to the number of cases, is 3 times what they've reported. So the use of Zipf's law can't get you something that isn't there. So what about COVID within the United States? Now here what we have are the number of cases per 100,000 in the population. But they're spaced by logs, so it's still a log of the number of cases, and it's the rank of the state with the rank the state with the most number of cases per 100,000 residents is North Dakota, and the second most is South Dakota, and then the rest of the states, there's 52 here, that includes DC and Puerto Rico, basically follow Zipf's law. It's a straight line, except at the bottom end where you see Vermont, Maine, and New Hampshire, which are also outliers. You can also look at some of these, Hawaii and others, but let's just focus on these 3 right now. Well, one of the things we know is that North and South Dakota that have an excessive outbreak have resisted public health restrictions, and they're dealing at this point with the aftermath of a motorcycle rally in the Dakotas, in which lots of people came from all over wearing no masks and carrying on. We also know that these states, Vermont, Maine, and New Hampshire, and the other adjacent New England states, have had strong restrictions on public gatherings and have had requirements for mask wearing. So what we found is that with very, very little work, I mean, ranking data isn't very hard, and then taking their log and making a plot gives you a great deal of information. The question is this statistics? And the practice of evidence-driven statistical and scientific investigation was developed by Fisher, Pearson, and Neyman, and others during the first half of the 20th century. And that changed the world and changed the way they did things. But in 1962, John Tukey published a prophetic paper called The Future of Data Analysis, in which he provides an epistemological justification for using a different outlook and a different set of tools for understanding the world. He provided the beginning of an epistemological justification for the atheoretical plotting of data in the search for suggestive patterns. That is, you make plots without theory and look for things that are interesting. And his term for such activities is exploratory data analysis, which he viewed as being detective work. The search for patterns yields two important results of interest. The pattern itself, which provides insight into the underlying structure that's exemplified by the data, and then the deviations from that pattern, which signal an aspect of the data that deserves special attention. So the first thing, the pattern itself, that's the compared to what. The two is what you're doing, what you're looking at. So the question we should address is whether the Zipf-informed displays of COVID are anecdotes or evidence of irregularity that we can harness for insight. Is the linearity in Zipf plots real or an artifact? But as we've seen, the relationship noted by Zipf holds so often that it's unnerving. Today's talk was as much about epistemology as about epidemiology. The epidemiological questions fall into two related categories: what's usual and what's unusual. The second question is critical for us to try to uncover what policies are harmful by studying those entities that are exhibiting unusually high COVID infection rates and contrasting them to the policies that are associated with entities that have especially low COVID rates. Obviously, we can't tell what's unusual without first establishing what's usual. Now, the epistemology is that exploratory data analysis is founded on the belief that the world is law-like. That is, there are patterns and consistencies that repay the effort to notice and describe them, and we should be open to discovering them in our data without preconceived assumptions. That belief underlies the physical, biological, and social sciences. Scientists have often first noticed regularities in patterns and anomalies, and then sought explanations. And then if you don't believe that the world is essentially law-like, you almost certainly don't want to practice statistics, because you'd be wasting your time describing, modeling, summarizing, and testing regularities that you didn't believe were real in the first place. What did we contribute with this paper? What we're offering here is a widely observable regularity that's easy to display and can be useful as a summary, especially for nominating outliers and identifying subgroups. It isn't theoretically deep, but if the Zipf pattern does describe most, but not all of your data, then you probably should look carefully at the cases that don't fit or the places where the linear pattern breaks. This method seems especially valuable for determining whether extreme values are too extreme at either end. At the end of the 19th century, Edna St. Vincent Millay wrote, "Upon this gifted age, in its dark hour, rains from the sky a meteoric shower of facts. They lie unquestioned, uncombined. Wisdom enough to leach us of our ill is daily spun, but there exists no loom to weave it into fabric." During the course of the COVID-19 pandemic, we received daily reports of the incidence of infections, recoveries, and deaths for countries of the world and subsections or states within countries. The accuracy of these reports is often unknown, but surely varies widely. To be able to understand this meteoric shower of facts, we need a loom to weave it into a fabric for comparison. In this talk, we've proposed using the regularities of Zipf's law and suggest that you can focus our attention on deviations from those regularities. The outlier detection literature is huge, and most methods attempt to estimate variability of the non-outlying points, fighting off the influence of the as yet unidentified outliers, and some require substantial computing. Zipf makes no assumptions. It has no pretensions. We propose it as a simple graphical loom on which to weave a useful fabric from the shower of facts about the pandemic. At a time when identifying extraordinary cases may help public health, simple, easily used methods may have value. We encourage you to use Zipf's law to examine data. It's often suggestive, it's inexpensive, and very easy to apply. Here are some references that here's what I referred to in the talk. The paper by Deborah Boca, Paul Velleman, and myself on this particular, that is this particular talk, will be coming out in the British journal Significance sometime shortly. Thank you very much.